In these next videos, we will really dig into the Fourier series. And after this week, I want all of you to be able to compute Fourier series and be very confident in doing so. During class time, we will do lots of exercises. And then here in the videos, in particular the next two, I will focus a bit more on the theory behind the Fourier series. And we will learn about Dirichlets theorem and about the Gibbs phenomenon. Dirichlets theorem has to do with convergence of Fourier series. You might remember in an earlier video I asked, when does this series converge? It is an infinite series, right? So this is a legitimate question. And Dirichlet theorem, honestly, I find quite beautiful. It gives a wonderful, I think, answer to this convergence question. So before we do this, I just want to recall piecewise smooth functions, PWS. Remember, piecewise continuous were functions which were continuous most of the time, and then they can have a few jumps. Piecewise smooth means that f and f prime are piecewise continuous, so both. For example, here is a function, f of x is x squared between 0 and 1, and it is x between minus 1 and 0. So let's just quickly plot this function. So here it is x, and then from 0 to 1 is x squared, so a parabola. So this would be the function f of x. And then the derivative is given right here. So in this, in the negative bit it is 1. In the positive part it is 2x. So this would be f prime of x. And you can clearly see actually f is even continuous at 0. F prime has a jump, but this is like a finite jump. So it's a well-defined piecewise continuous derivative. Here's another example where this is not the case. So this function f is x to the 2/3. Let me plot this as well. So this will look something like this. So it has a little dimple here at 0, and it's supposed to be symmetric. Now the derivative then will go to minus infinity here and come from plus infinity there. So this is f of x. This is f prime. And you see f prime has basically an infinite jump from minus to plus infinity. This is not a jump in our sense. So this f prime would not be piecewise continuous. So this is a bad example. So if I do Dirichlet theorem now, think about the first case where we just have jumps. Dirichlet's theorem. So let f be piecewise smooth on a symmetric interval. So now we go from minus L to L. And then we have the Fourier series like we computed a few already. Coefficients a0, an, bn, and then cosine and sine terms. And the coefficients can be found by these integration rules, which we have seen as well. So now we collect, I think, about 3 properties of the Fourier series. So here's the first one. So let's assume x0 is a point where f is continuous. So f is continuous at x0. Then the Fourier series equals the function. So at each point where there are no jumps, the Fourier series equals the function. So this is already absolutely super. But now what happens on the jumps? This is here in item 2. If we have a jump discontinuity at x0, then the Fourier series will jump to the mean value. Okay, so easily illustrated. I don't have much space here, but I think I can still illustrate this easily. So let's say the function has a jump here, from here to here, a finite jump, all right? Then the Fourier series, so this guy, will attain the middle value between the jump. So maybe in my graph it is a little bit below the axis. So this is where the Fourier series will end up. On the curves, so maybe here, we saw under item 1 that the Fourier series equals the function. So the interesting part really happens only at the jump, and then this says we jump exactly halfway. Cool, very cool. And then the same is true for the endpoints. This would be item 3. So this is the mean between left and right. So what I mean, I need to explain a little bit better. Right, we are looking at a function from minus L to L. And whatever, let's maybe do something like this. Hyperbolic tangent or so. So now the question is, what is the value at L? Function is not defined at L, so the value of L turns out to be exactly the half between the right-sided limit on the left and the left-sided limit on the right. Sounds complicated, but what you do is you, in your mind, extend the function periodically. So then you get beautiful jumps here, and then you know that the Fourier series will jump exactly to the middle of this jump, and then here as well, and here as well, right? So I think graphically the theorem is even easier to understand than using formulas. Okay, all in all, then we write f of x0 is approximated by the Fourier series with this understanding that at jumps, we actually always jump to the middle value. The Fourier series always jumps to the middle value. No other choice. Let me do one example, and this is an example we have seen already using the linear function. So I look at the linear function, f of x is equal to x on the interval from minus L to L. Let me plot this once more. Now I want to choose a color differently, so this is minus L, and this is L, and then this is 2L and 3L. Okay, so here between minus L and L we have the linear function going from there to there. Fine. And now the Fourier series makes it periodic, so you get a periodic extension, meaning you take the same function and plot it here again, and then you take the same function, plot it there again, and also for the negative. And then you see what you should expect, right? So you should expect at the jump, the Fourier series should end up right on the axis. So the picture is not very exact, but you should jump right to the middle, which in this case is actually 0. We did compute the Fourier series already. So this was the formula 2L divided by pi, and then the sum of the minus 1 to the n plus 1 over n sine n by x divided by L. So now let's use Dirichlets theorem. Let's do what I just did there in the plot. Now mathematically, we take the periodic extension f bar and evaluate it at L from the right. So here we are now at this point, and there the function is minus L. If we look at the periodic extension at L from the left, we are up here, and we get plus L. So this means then the mean value of these points, this would be here, is minus L plus L divided by 2, so the mean value is 0, so that is a point indicated already here. Oh yeah, and then here is kind of a graphical representation of the same function, where we included these points here, where the jump occurs. That's cool, isn't it? A very funny thing happens if we take this series now and evaluate it at certain points. For example, if we evaluate this at L half. So here is L half, and so then the function would also be L half. So I sub in L half here and here, and now I show you what we get. So we're going to take x is L half, we sub it in, f of L half, which is also equal to L half, of course. So then we have L half here. And then this becomes the sine of n pi over 2, because we submitted L half and then the L would cancel. Now look how the sine function looks like. Okay, so this is the sine wave, and then these zeros are at pi and at 2 pi and 3 pi and so on. So then the pi halves are right in between, right? This would be pi half, 2 pi half, 3 pi half, 4 pi half, 5 pi half, and so on and so on. You can count them through. So meaning this expression here, sine of n pi half, is first it is 0, then it's 1, then it's 0, then it's minus 1, then it's 0, then it's 1, then it's 0, then it's minus 1, 0, 1, 0, minus 1, and so on and so on. And now there's a fancy way to write this down. So whenever the index n is even, we get zeros, okay? So this would be at 0, pi, 2 pi, 3 pi. So then we split it up for the odd indices, which have the form 2n minus 1. And here we have the even indices, which have the form 2n. You see, and then you get a sine n pi, which of course is always 0. So this term is gone. This other term, this is a minus 1 to the n plus 1. And so then we shift the sum by one index, okay, and then we finally get this formula here. So pi quarters is minus 1 to the n to n plus 1. And now all mathematicians get completely excited because this is an explicit formula for pi. Or pi quarters, but then you multiply by 4, so you have a formula for pi. So this is known, this is written down here again. Pi quarters is 1 minus a third plus a fifth minus a seventh plus a ninth minus 1/11th. And this is known as Leibniz formula for pi quarters. Isn't that a cool formula?